I'm not doing this aspect of the problem.
Yeah, that's what I'm saying. But you didn't.
We already solved it.
That's what I'm saying.
We already did. We have the answer. Okay? So our new problem is to find this wave function that fits this initial condition we did. Everybody okay?
So these conditions are new though, right?
What's that?
These initial conditions are just like you didn't use those. You didn't use these to find. Okay, all right.
Well, the initial conditions are all the same. The only thing that's different is the wave function itself.
That it started out with, yeah. The initial condition, so we prepared this wave function like this. We said, hey, this is what it looks like to begin with. And so, this is nothing new. This just says that the total wave function as a function of time can be built as a linear combination of the infinite basis set. Okay? So now our only job is to find what?
See you then.
The CNs. All right? And so the CNs are going to equal what?
It's going to be an integral.
This is when we did Fourier's trick. So Cn is going to equal. Is it going to equal an integral or anything like that? Don't we need the integral for Fourier's trick? Did you guys do the example problem in the homework problem? Because this is what you have to do.
Oh, is it radical 2 over A?
So you guys are confusing details for understanding what we're doing, I think. All right? So this was Fourier's trick, the very last thing we did. All right, and it comes out to equal the integral of capital psi of x in t equals 0 times the basis at time equals 0 times psi n of x in t equals 0 dx.
Which is just the square root of 2 over A sine n pi x over A.
Yeah, we've got to go and do all that stuff, yeah. Everybody okay? So we did that by Fourier's trick. Anybody recall what Fourier's trick is here? You multiply both sides by capital psi not of n, but capital psi of m. And then you integrate both sides, right? And then what happens to the psi n and the psi m dx on this side?
Function where if n and m are not equal,
You get a delta function.
n and m are equal as 1.
And why is it? And then you get the delta function on the integral because why?
Vector dot product.
It's like a vector dot product, but it's a function space dot product. And what we're saying is that psi n's and psi m's are linearly independent from each other, so it's like the dot product of 0. So then what drops out over here is you're going to get an integral over here, psi n and psi m dx. But the only place where that integral is going to be non-vanishing is when n equals m. And when n equals m, that integral goes to
0.
not 0. When n equals m,
Goes to 1.
it goes to 1. Oh, you're left with the Cn. You're left with the summation of all those. But the only one that survives is when n equals m, so you're left with Cn on this side. And then on this side, you're left with a psi of x of t times psi n of x and t dx. All right. The only kicker that we put in is that very early on, Griffith showed that if you normalize the wave function at time equals 0, you've normalized it for all of time.
That's section 1.4.
Yeah, Mike was doing that one, yeah. All right? So what you do is you solve this whole thing, but you solve for time equals 0, and you can solve for CNs. Okay, this is exactly example problem 2.2, right? This is exactly the homework problem 2.7. Are we all on track now? Better?
Better.
Because this is the whole procedure for the whole course. Alright, other than formalism at some point. Alright? Alright, so let's do this problem. Let's try to knock off this problem. The first thing that I have to do is my wave function at time equals 0, my initial one, is this finished yet? Like, is that exactly right, just leaving it like that function?
We need to know A, right?
We need to know A. Why do we need to know A?
Gotta normalize it.
We've got to normalize it. Okay? So the first step is that we've got to normalize, this. So step 1, normalize this. Okay, so how are we going to normalize that? So normalize psi. So what do?
You gotta integrate the psi of x t equals 0 squared. Perhaps.
Has to equal 1. Alright, so how do we do that integral?
From 0 to a over 2 integrate for 5a, and then for a over 2 to a, it's negative 5a.
Yeah. So let's do it. This breaks down into the integral from 0 to a over 2 of what's going to be here.
5a.
Okay, is it 5a?
25 A squared.
Okay, so it's 25, so it's 5 squared a squared dx, right? Then what?
Plus the integral from a over 2 to a of negative 5 squared.
Okay, it's minus 5 squared, but minus 5 squared is going to be 5 times a squared dx. Set that up. I put this equals n, but clearly I meant to say that equals 1, because you want to normalize it, right?
Yes.
Okay, so when you do this integral, you guys I trust can do this. Alright, I got something like this, and you should check it out. I just did this in the side notes in my book, so you should check it out at home, make sure everything's cool. But I got that A equals capital A. What I got from this is that capital A, the normalization constant, equals 1 over 5 times the square root of A. I want to make another point before we go too far ahead. All right? Does anybody have any predictions on what these CNs might look like? So look at my initial conditions. And the CNs are basis, are the projections onto a given basis. What do the basis solutions look like? They're the solutions. They're the solutions to the 1D, the infinite 1D well, right? The first one looks like what?
Just half a wave,
Like a half a wave. What does the next solution look like?
a full wave.
It looks like
Two bumps.
one sine, right? And then the next solution looks like
1.5.
3 pi,
something
4
more,
pi.
right? So we're going to predict that whatever happens here, our solution is going to be a lot of which one? The sine, right?
A lot of sign, right?
N equals 2, right? The N equals 2. Everybody okay?
Like 4 and 6, all the even things.
Okay, good. So as long as you're thinking about that, that's where we're going to go. Okay. So
Right.
what's the next step?
Plug both that equation, plug the x of t
Okay, so we're done.
into the CMN equation.
Okay, so now we go over the CNs. And the CNs are going to equal the integral from minus infinity to plus infinity of psi of xt equals 0, which we'll write as a step again. The step function is 5 times 1 over 5 square root of a for 0 less than or equal to a over 2. And then it's going to be minus 5 times 1 over 5 the square root of a for a over 2 less than or equal to a. Alright, we're going to do that, and then we're going to, because that's the side of time equals 0, and then what does it multiply by?
The square root of 2 over a sine n pi x over a.
Yeah, so I'll do it explicitly. It's going to be 1 because at time equals 0, that time independent part comes out to be 1. Right? And then, as David said, it's going to be the sine of n pi x over a dx. All right, so can you do this integral?
Yes.
How are you going to do the integral?
Split the divide. Take the function.
Break it into two.
Break it into 2 parts to go from 0 to a over 2, and then from a over 2 to a.
Okay, so this is going to look like the integral. So from minus infinity to 0, the wave function is 0. All right, so we're going to go the integral from 0 to a over 2 of 1 over radical a times, I needed the normalization constant over here too.
2 over a.
Yeah, I forgot that. Sorry, guys. So it's 1, and then it's going to be radical 2 over a.
Why is there 1 there again?
So we're plugging in the psi n of x and t, and psi n, capital psi n, is the time-dependent part. But at time equals 0 is e to the 0, so that's a 1, and then we're just left with the spatial part. And the whole idea there is we're kind of doing everything at time equals 0, and then the cn's a constant for all the time.
So we're saying how if it were depending on, so if it were dependent on time, then we'd be able to plug that in there, but it's not.
If it was dependent on time, then we could still solve for 0 just to get the Cn, and then we can do whatever we want to do with time after.
Yeah, in this technique, it's all time independent. The CNs are, what we're doing is we're using stationary state solutions, which are time independent, as our basis set.
So we do it as if.
All right. So when we do this integral, it's this thing times radical 2 over a times sine n pi x over a dx plus the integral from a over 2 to a of minus 1 over radical 2 over a sine n pi x over a dx. Okay, how do you do these integrals?
We can take it. We'll put the radical 2 over a in front.
Okay, you can do that, take care of the constants. But, Allenmeyer said what I was looking for by substitutions. So the way I do this integral, I do a substitution. All right, and then what I do is I reevaluate what the limit should be. Okay, so for example, here, I'll say let p equal n pi over ax, then dp dx equals n pi over a dx. So in other words, dp over n pi over a equals dx. All right, but as soon as I define my new, so you guys have to, I don't know how you guys want to do it, but guess what? You got to get it right or wrong when you do your integration.
It's got to be right.
You got to get it right. I don't care how you do it, but get it right. So here's what I did. After I kind of did it close together, but as soon as I define a new variable, p, then what I do is I set new limits. So when, let's see. So when x equals 0, what is p?
0.
0. When x equals a over 2, what is this?
N pi over 2.
This is n pi over 2. Okay? So I would rewrite this integral. This equals the integral from 0 to n pi over 2